So welcome to the seventh week of Fundamentals of Additive Manufacturing Technology. So today we'll be discussing on fuse deposition modeling. Let's start with the first question. So which of the following is the correct procedure or process for FDM process? This is actually procedure. Let me just correct it. Okay, so which of the following is the correct procedure for FDM process? Um, so it's quite straight. As we know, FDM process has but some particular steps like creation of a CAD model, then converting to STL file, orientation of the STL file, generation of support, then slicing, then area filling, then generation of G code, then deposition of buffer layer, and deposition of main and support material, then finally removal of support, and then surface finishing. So according to this, the option C is correct, like which is creation of CAD model, then according to the options here, slicing, then area filling, then generation of G code, and then deposition of buffer layers. I'll just for a brief process steps. Creation of CAD model, converting to STL file, orientation of the STL file, I'm sorry, like till now, whatever I was speaking, I think it was not audible. I'm sorry, I had muted it. So, if any such issues come, you can just point out. So, I'll again repeat it that the correct process for FDM process is option C, and I'm just outlining the steps. Generation of support, slicing, then we have slicing, area filling, generation of G code, deposition of buffer layers, deposition of main and support material, removal of support, surface finishing. So, according to this, creation of CAD model you can do in like any softwares. Suppose let's take up the example of a SolidWorks, and while after preparing the CAD model, you will convert it into a STL file, save it in a .stl format. Then you will import that STL format to any your slicing software like Ultimaker, Cura, or Flash Print or anything, and there you will do the orientation of the STL file, like how do you want that STL file to be printed in your in your machine. So for that you will have to put it in a proper, on the platform in a proper XYZ direction. And then if suppose you have some overhanging in your STL file, okay, suppose some parts which are in Z direction you want to print it. So for that you need to generate some supports. There are various supports like tree support, tree type support, branch support, linear support. After that you will do the slicing. Slicing means now the slicing software, okay, it will take generate, it will give you some report not exactly, but some data like how much time will the machine take for machine take the STL file to be printed, 3D printed. So what will happen is it will show you the layers, how many layers are involved, and this is based on the parameters which you have provided according to the various parameters which you have provided in the slicing software. Next is the software will generate G codes, which is now understood by the 3D printer, and after that the your specimen or sample is printed, and further after that removing the, after the printing is done you remove the supports and you do the final finishing. These are the processes involved in a FDM process. Buffer layer means like suppose we have a specimen, okay, and now we have this rafts, we have some base support which we not support, base extra additional layer which is given by the printer so that the specimen can be printed properly. It can be raft, brim, these all things are the buffer layers. And while the printing is started, the printer what it does is it gives a specific layer, just some specific little bit additional layer, so that suppose some unwanted filament will be coming out of the nozzle, that will be removed. And specifically the buffer layer means the raft or brim, so that while raft is the additional layer below the specimen, this will be given so that when you remove the specimen mm, from the 3D printer machine, your samples won't get damaged. That is the advantage of raft. Also, it gives additional strength and support. No, support is for the overhanging parts. Like suppose if you are printing some structures which are which do not have the projection towards the z-axis. Okay, so in that case you can give additional support and later on you can remove it. It doesn't have this, it is not included in your CAD model that is generated by the slicing software. Okay, is it clear? Can we move forward? Yeah. So in the next question, in the pinch roller mechanism, what will happen if the friction factor is less than 1? So as you will be having an idea what is, yes, yes, crushing, filament is crushed by the rollers. So as we know, friction kf is the friction factor between the rollers and the filament. So when kf, no, I'll write it here itself. When kf is greater than 1, filament is greater than 1, filament is crushed by the rollers. Kf is less than 1, filament slips between the rollers, and this is the ideal condition. So as in the question it is written, what will happen if the friction factor is less than 1? That means filament slips between the rollers. Option B is the correct answer. Is the correct option B is the correct answer. And for just uh, BF is equal to KF. VF is equal to KF 4Q by pi d square F. This is the formula for the filament feed rate. This is the formula for the filament feed rate. Now, here VF is equal to filament feed rate. Q is the flow rate, and DF is the diameter. And this Q, this depends on build conditions, which are thickness, width, layer thickness, bead width, and transfer speed. So moving on to the next question. Staircase effect is visible in which of the following processes and why? So we see staircase effect in FDM processes. Now is the correct option. In the shape deposition manufacturing, we see segments. I think whatever it was writing was not visible to you, so I'll again write it. So SDM, this does not use conventional slicing. So here we use like segmenting. So what happens here is in SDM we have that the model is visible and the model is made, and if the model is invisible the support is made. So here the model and support materials are created alternatively. That is it. This involves both deposition and machining, so it is a hybrid process. So its slicing makes use of visibility concepts. This therefore this part is free from staircase effect. Like that is it this SDM, it matches with the original geometry. Here slicing makes use of visibility concepts. Therefore, the part is free from staircase effect. So I think like all are till now aware of what is slicing. Mm, like till now you know that our CAD model is processed in a slicing software where we are giving various parameters which the machine 3D printer machine will understand. And from the slicing software, as I already said, the STL file is converted into a format of G code, .g code file, which .gx file, which is imported into the 3D printing machine. So in this slicing software, what we will provide all various parameters. Like the parameters can be what will be your uh, whether you want to give any supports, any additional layers such as raft or BIM, what is the percentage of density you want, how much uh, how much each layer size, what are the starting layer sizes, what are the ending layer sizes, these and various other parameters you can give in slicing. So in the SDM process we do not have this staircase effect, while in FDM process, fuse deposition modeling, we can see a large amount of staircase effect. Yes. Mm-hmm. Yes. So, So yes, this is there. But suppose if, as you're talking in FDM process, okay, I'll just give you a simple scenario. Let's take a flash print software. Okay, so this is a software for the Flash Forge company. So here, what you are doing, you are processing, taking a STL file from SolidWorks. Okay, you have taken the CAD model. Then now you are importing this in that flash print software. Now in that flash print software, you are giving all other parameters. Okay, and when you save it, so there you do not need to provide any. You don't need to provide any codes. Okay, what is that software and only save it directly in .gx format. Okay, so this is not about that G code M code. So I'm just saying that it will automatically give it. Okay, so you don't need to worry about that G code M code. It is there obviously. And regarding the temperature which you are saying, so depending on the 3D printer machine which you are using, what will happen is you will input the material. Suppose you are using, since it is FDM, I'm going for polymers. So you will be using ABS polymer, PLA polymer, any um, these polymers. So what will happen depending on the type of polymer, the uh, there are already predefined temperatures, okay, for the polymers, like 190 for PLA, 230 for ABS. So automatically the machine will take those, or software will assign that predefined temperature. So this is the like practical and experimental way in which we do the slicing. Okay. So if this is clear, we'll move on to the next question. So when polymer melts, leading to radial expansion of the melt, this process is called as which of the following? So we know that we have various method processes like bead ironing, die swelling, bead spreading, bead rolling. So the radial expansion of the melt in a polymer is called as which of the following? So it is die swelling. So now we'll discuss briefly a little about all these methods: dye swelling, bead ironing, bead spreading, bead rolling. Okay. So what is dye swelling? When, like, this is the build material which is melting. This is the heated liquefier, and this is the print nozzle. Now this is the B2, this is the B3. Now what will happen is, when now the polymer material is under stress, so some part of the deformation energy is being stored elastically. So when the polymer which is melting is no longer constrained by these walls of the liquefier, and the stresses which were acting on the melt in the nozzle, these are relaxed. So the stored energy, it will be released. This leads to radial expansion, which is here. This leads to this radial expansion of the melt, which is referred to as dye swelling. Okay. So what is happening is the stored energy, which is no longer like the material is no longer now constrained by the walls. Now this stored energy is lead this leads to radial expansion of the melt, which is known as dye swelling. As the name suggests, it is now swelling. That is why it is dye swelling. And the swelling ratio, which is D3 by D2. That is the diameter of the die opening to the diameter of the extruded material. That is the swelling ratio, S. Now next is bead ironing. Bead ironing, bead spreading, bead rolling. So when the print head nozzle, in what happens in bead ironing is, you have the print head nozzle. It is in contact with the deposited bed, and now it is in more stable flow and ensuring a very flat surface. So now bead in die swelling we have the swelled portion, but in the bead ironing we have a very flat, and a flat the bead will spread into an oblong shape with the spreading rate, and the final shape that depends on the viscosity of the melt and the surface energy also. Next is your bead spreading and bead rolling. Now bead spreading, it is like very nicely yeah, yes. See, there is never the direct contact within. There won't be a direct. There will be some amount of always a little bit buffer between the nozzle and the print area. If there will be contact, what will happen? That there will be no. It will never get printed properly. Okay. So there will be always some amount when you will be setting the nozzle. Okay. So what you will do is, every time when you start printing or using the machine, or not every time but at least frequently, uh, every 4 to 5 times of printing, you will always do the calibration of your print bed. Okay. So when you do the calibration of a print bed, what we are doing is we are trying to see whether the nozzle is properly calibrated. If it is not properly calibrated, what it will happen is it will always give bad printing errors. Like the print surface will never be printed properly. There will be some issues. Nozzle will be clogged because there won't be enough space for you to print. So that is why we always give some amount of buffer according to your requirement. And also we always check the printed velocity also. Suppose the printed velocity is very large, the bead will become unstable and discontinuous. So yes, yes. Okay, wait, I'll just check the question. Yes, yes. Okay. So what is your doubt exactly? It's a pretty straight question. Hello. So yeah, it is asking about, yeah. Okay, the correct answer is option A, because uh, exactly what happens is there is no direct contact. Like there, obviously the nozzle and the bread will, they have to, the nozzle, whatever the filament will be coming out, it will be coming out from the nozzle and getting on the bed. Okay, print bed. But thing is, what I meant to say is there will be no physical contact, obviously. Like the nozzle won't be touching the bed. But that doesn't mean that bead ironing, it won't have a contact. There will be contact between the nozzle and the bed. But as I'm just imagine your pen, okay, and you will be touching the tip of the pen with the your table. No, the some filament, just imagine that some filament is coming out of your pen and it is falling on the table. So in that way contact, I meant to say. Okay, I hope it is clear. Okay. uh, like bead ironing, it just let me check what is mentioned in that our lecture, so that it won't have further confusion. Is it mentioned anywhere direct contact? Okay, okay, okay. Okay, so moving on to the next question. In FDM process, the bead area varies according to which of the following? So, mm, uh, so what happens is the correct answer is Weber's number and Reynolds number. But I'll explain exactly what is happening here. Weber's number, Reynolds number. So, so we have the critical velocity. Okay, critical velocity, which is given by the formula pi square d2 by 2 delta p by 8 eta L square h square. 。  Now, Now when what happens is when these liquid properties, so this is a filament, okay, it comes out, this is it comes, the filament comes out. Now this is the H height which we take. This is the print bed. This is the print bed. This is the height. Now this H is this. So what is so when the flow is coming through the print nozzle, now this is the region 1, region 2. Okay. Now when the flow is coming through the print nozzle, so these are the various liquid properties. These are not directly involved in the stability limit which is present in this equation. Now when the impact which exceeds the stability limit and the ability of the material to knock down from AB to AB minimum, like the AB varies based on the Weber's and Reynolds number. Now how it is coming out? What is this AB and AB minimum? Now that we'll discuss. Now AB is the cross-sectional area of the bead, which is inversely proportional to the velocity of the print head. Now this is the flow rate, volumetric flow rate, and this is the velocity of the print head. Now, after leaving the liquefier nozzle in a melt extrusion additive manufacturing process, the bead of the polymer melt, it lands on the substrate or a previously printed melt of bead of polymer. Now, when it passes through a print nozzle, that so we have a volumetric flow rate. Okay, so this volumetric flow rate, here the cross sectional area of the bead is inversely proportional. Now, when the print head is sufficiently large, the bead will become unstable and discontinuous. Now, the maximum achievable area at the maximum head speed is similar to the, like it is stable up to a height limit on the order. Okay, this AB minimum is equal to x square by pi. What this means is it is the maximum head speed. This is achieved, which is stable up to a height limit on the order of the square of the tip height above the surface divided by pi. So this is the AB minimum, which we have already discussed. Like suppose this is the head speed. Okay, this is the this is the head speed. Now this is the h square by pi. Now the critical velocity, as we know, this is given by this formula. So when the liquid properties are not directly involved in the stability limit which is present in this equation, the impact of exceeding this, when we exceed this stability limit, and the ability of the material to neck down from this AB to AB minimum, that this, when the material will come to this uh, cross-sectional area velocity from AB to AB minimum, those parameters are given by the Reynolds number and Weber's number. So Prandtl's number, Euler's number, it is just given in the question for confusion. These are the two numbers which are followed, these parameters for the bead to come from AB to AB minimum. Okay, so moving to the next question. How is the cross-sectional area of the bead related to the velocity of the printed in FDM process? This already I said it, so I'll expect the answer. This is pretty straight. AB is equal to Q by VT. Now at least some of you can answer. Okay, the cross-section, yeah, inversely proportional. So as I already said, A Q is the volumetric flow rate, AB is the cross-sectional area, of the bead, and V is the velocity of the printhead. Also, I would like to discuss here. Now we know that cross-section area of the bead is inversely proportional to the velocity of the printhead. So here AB is equal to Q by Vt, or AB is equal to, if we can put the substitute, so it will be pi d2 square d2 by 2 whole to the power 4 delta P by 8 eta L2 Vt. Okay, so here as we have already seen, okay, so velocity is not constant in the beginning and the end. In other words, velocity varies. No, velocity, sorry for the interruption. Velocity varies at the start and stop of each successive layer, as well as when there are sharp turns in the tool path. So what is exactly the meaning is, we know that suppose this is the, what I will, I'm sorry for the bad diagram. Suppose when we are like, this is, okay, so what will happen is, this is a graph. Okay, this is the extruded portion of the filament. The filament goes from here to here. Now this is the VB. Let's do VB, and this is the flow rate. This is the flow rate, and this is the velocity. Now this is the start position. This is the stop position. So what will happen is, this this portion, it is under dip. This is under deposition, and this is normal deposition, and this is, here we can say, over deposition. Now here we have, when over deposition is there, we have decelerating printhead. Here we have steady printhead velocity. And here we have accelerating printhead velocity. So what I mean to say is, as you can see, its area. When the area is less, accelerating printed velocity, and normal, steady printed velocity. And when it is over deposition, we have decrease in printed velocity. So that how this is also a way of proving that it is inversely proportional to the velocity of the print. Okay, so moving on to the next question. In FDM process, the cooling process of a single filament follows which heat transfer model? Well, the FDM process, the cooling process of a single filament, yeah, it is one-dimensional transient heat transfer model. So, we can say that it is simplified into one-dimensional transient heat transfer model. Like a single deposition is considered as a one-dimensional block. Now, the head moves at a constant speed of v along the x-axis while extruding, and uh, this conduction heat transfer with the, it can also be said to as in the form of, considered in the form of convection, because the mass of the foundation is much higher than the filament, and the conduction at the interface would not change with the temperature. So here it is known as the one dimensional heat transfer model. Um okay, so let's move on to the next question. Use of inelastic fillers such as ceramic particles or carbon fibers tend to reduce which effect? Yeah, yeah. This is seen in, this is done in dye swelling. Correct. Okay. So are there any further doubts which we can discuss since some time is left? Assignment? Like 7, right? Question number 6. Okay. Typical thermo. This is a a very straight question. Shear thinning behavior. This is like directly written also in the lectures. If you can go through the lecture one, the first lecture of FDM first lecture. So it in that video, it can you can get the detailed explanation. I think you all are aware of what is a shear thinning, shear thickening, and Newtonian behavior. So shear thinning, what happens is can anyone say like what happens in a shear thinning? Okay, so in shear thinning, velocity decreases with increasing shear rate. Okay, so thermoplastic materials used in FDM, they usually show shear thinning behavior. That is the viscosity. Viscosity decreases as the shear rate increases. Viscosity decreases. Now, this is suppose if we take the power law. So we there have a formula, tau is equal to gamma dot by phi to the power 1 by n. So here the gamma dot is the shear rate, m is the flow exponent, and phi is the fluidity material constant. And this is general characteristic. This is given by the Newtonian behavior. As you must be remembering, we have a shear stress and shear rate, where we have the dilated Newtonian pseudoplastic Bingham pseudoplastic. Those were the uh, various behaviors of a fluid. So for the FDM process, we follow the shear thinning behavior. Okay, so yes. I'm not sure which question I'm asking. Can you just tell me the question number? Okay. You can, I can't, you can get it. I think whatever you can, this is a direct question, and I think the dates are not over. So, yes, this is, you have to find out. Okay, so any more further questions? Okay, so if there are no further questions, we'll end the session. Thank you for attending the session. So let's meet next week. Okay. Yeah, all the best for the assignments.